Hi, today I'll be telling you about the square root of 2. Specifically, I'll be telling you about how to prove that the square root of 2 is an irrational number. So firstly, before we move on to anything, let's see about how the square root of 2 was found. Well, I consider it as a misfortunate number, and it goes back a long time to ancient Greece. It was first known to have been found by the school of Pythagoras. And as I've told you about how it was a misfortunate number, it was a number that brought death. One of Pythagoras' disciples found a number that went against what they believed in, and so they drowned him, so that their principles would remain right. This number that they found was the square root of 2. And as it was unlike any other number that was introduced, it was a number that couldn't be shown as a fraction, and so it had to be grouped into a whole new category of irrational numbers. So let's take a look at rational and irrational numbers. Before the square root of 2 was found, the only numbers that people thought of were rational numbers. And these rational numbers were numbers that can always be represented as a fraction. They include integers such as 1, 2, 3, or fractions such as 2/3 or 3/3. But people discovered over time a number that couldn't be shown as a fraction: irrational numbers. And this whole new numbers that they found expanded the area of math, creating what we now call as real numbers. With these real numbers include both rational and irrational numbers. Also, the beginning of the recognition of square root of 2 has also increased our knowledge of infinite and how there could be different sizes of infinite sets. And the examples of irrational numbers would be some numbers such as the square root of 2 or the square root of 3, as well as e or pi. So how can we actually find the square root of 2? Well, let's first draw a square of side length 1. And I'll draw a diagonal in the square. And to find the length of the diagonal, we'll use the Pythagorean theorem, which is that a squared plus b squared equals c squared. And if we apply that to the square we have right now, we have the equation that 1 squared plus 1 squared equals the square of the diagonal. And the square of the diagonal has to be 2, and therefore the diagonal length has to be the square root of 2. And so we've been able to find out how to actually find the square root of 2. Now let's move on to why the square root of 2 is irrational, and I'll first prove it by solving it as an algebraic way. So let's first pretend that we don't know what irrational is, and we'll pretend that square root of 2 is a rational number, and a rational number can always be presented as a fraction. So we'll set the equation as square root of 2 equals p over q. And p and q have to be both integers as well as being co-prime with each other. And being co-prime with each other means that their only common divisor is 1. So moving back to the equation. Now with this equation, I don't like any fractions, so let's multiply it by q so that we can get rid of the fractions. And by doing so, we get the equation q multiplied by square root of 2 equals p. And since we don't know what the square root of 2 is, let's get rid of it by squaring the equation. And so the final is that 2 multiplied by q squared equals p squared. So we have the equation 2 multiplied by q squared equals p squared. But if we look at the properties that make a number rational, q and p, when in the forms of p over q, a rational number should have co-prime denominator and numerator. But clearly, in this equation, p and q have to have a common divisor other than 1 that allows the equation to take place. If they were co-prime, the numbers wouldn't be equal by simply multiplying an integer. Okay, so let's take it a step further and prove that every possibility of the square root of 2 being a rational number can't occur. So looking closely at the equation, we find that the equation 2 multiplied by q squared equals p squared. And so here, p can either be an odd number or an even number. And so let's take a look first at p being an odd number. If p is an odd number, the right side of the equation has to be odd, as odd multiplied by odd, another odd, is always an odd number. So we find the right side of the equation is odd, and let's look at the left side of the equation. The left side of the equation involves 2 multiplied by a number. But if a number is multiplied by 2, it is always that it is an even number. So we find an equation where the left side is even, but where the right side is odd. This contradicts each other, as no number can be even and odd at the same time. So this leaves us with only one other solution, which is that p has to be an even number. And so let's look at the right side again, where it's p squared. And so because it's 2 times something squared, the p squared has to be a multiple of 4. But on the left side, we only have 1 2, so it means that q squared has to be a multiple of 4 as well. Multiple of 2 as well. But this clearly contradicts the idea that p and q has to be co-prime with each other, because obviously if p and q are both even, they have another divisor other than 1, which is 2. So we finally are able to prove that the square root of 2 cannot be a rational number. So we've been able to prove that the square root of 2 is irrational by using an algebraic way. But we can use a geometric way to find that the square root of 2 is irrational. And for us to actually prove it geometrically, of course, we need a shape, right? So let's draw an isosceles triangle. And I'll name it triangle ABC. And we'll pretend that the right triangle, the triangle ABC that I created, has the smallest integer sides, m and n. And the ratio of m and n has to be 1 over square root of 2, which is what we proved and made during the second slide. But if we move the side AB to AB prime, we can create another integer length of B prime C. And because I want to create another isosceles triangle with the same length AB at same length M, I'll rotate AB prime 90 degrees so that we can actually create another isosceles called AB prime C prime. And it's going to go through BC at D. Okay, so let's take a look at BC prime and BD. We've been able to create 2 congruent triangles, 2 congruent right triangles, AB prime C prime and ABC. But we also have another isosceles right triangle, which is triangle BDC prime. And so we'll take a look at the sides, and if we take a look at BC prime, we find that BC prime is AC prime minus AB. AC prime is the same as AC, which is N, and AB is M. So therefore, BC prime is N minus M, and BD, because of the angles shown, has to be N minus M as well. But this contradicts with what we've set out as NMM, as we've been setting out NMM as the smallest integers, but we see an even more smaller integer, which is N minus M. Because clearly, if you minus an integer from an integer, it has to be an integer as well. So we find that setting the square root of 2 as an integer contradicts each other, and therefore, the square root of 2 cannot be considered a rational number. Therefore, the square root of 2 has to be an irrational number. Now, hopefully, you're able to prove that the square root of 2 is irrational using both algebraic and geometric ways. I hope you enjoyed the video, and thank you for watching.